In this video, we are going to see some examples for mathematical induction. The principle of mathematical induction are essential because suppose if we assume a statement as P of n, which we want to prove that it is true for n an integer. Even if we are trying to prove that for several cases like P of 0, P of 1, etc., P of k, we are not able to accomplish this or complete this completely because if k is quite large, then it is impossible for us to prove it. So we need to use different technique to prove this principle of mathematical induction, where we use the general claim as P of n, and in order to prove that the claim holds for every n, we have to use two different steps, two properties has to be proved. The first one is the initial condition has to be proved. If n is 0, we have to show that P of 0 is true. Or if n is 1, then we will be proving P of 1 is true. And the inductive step is that assume P of k is true. That is, you assume that this hypothesis, induction hypothesis, P of k is true. Using that hypothesis, you show that the next stage, P of k plus 1, is also true. Let's understand this principle of mathematical induction when we are trying to prove a formula or a problem. Let us try to prove that sum of the squares of the first n terms, that is 1 squared plus 2 squared plus 3 squared, etc., plus n squared, is nothing but n into 2n plus 1 into n plus 1 by 6 for every n greater than or equal to 1. So this is in fact a formula. We are trying to prove this formula using mathematical induction. So if we want to prove this mathematical induction, first we have to use a notation P of n, which is the claim. So the claim is this identity is true. So P of n is 1 squared plus 2 squared plus 3 squared plus n squared as n 2n plus 1 n plus 1 by 6. We have to prove the base condition. The base case is n is equal to 1. So the left hand side of this identity is 1 squared, which is 1. The right hand side of this identity is also 1 because it is 1 into 2 plus 1 into 1 plus 1 by 6, which is 3 times 2 by 6, which is 1, that is true. For an inductive case, assume that the hypothesis P of k is true. The inductive hypothesis is true. So we are assuming that P of n when n is equal to k is true. We have to prove this result for k plus 1. So if we are taking the left hand side of P of k plus 1, with all those k results of P of k, we have to add the next element k plus 1 the whole squared. So that will be the sum of those first k terms, which is nothing but using the hypothesis, it is k 2k plus 1 into k plus 1 by 6, plus the last term k plus 1 the whole squared. In this, if I am pulling k plus 1 outside, then I get this is k plus 1 into 2k squared plus 7k plus 6 divided by 6, or this is nothing but k plus 1 into 2k plus 3 k plus 2 divided by 6. So the result 1 squared plus 2 squared, etc., n squared is n to n plus 1 n plus 1 by 6 is true. For the second example, let us try to prove that 1 into 1 factorial plus 2 into 2 factorial, etc., n into n factorial is n plus 1 factorial minus 1 for every n greater than or equal to 1. So the claim here is this identity is true, so we have to take that as P of n. And the initial condition is n equal to 1. So base case is n is equal to 1. And we have to check whether it is true. The left hand side is 1 into 1 factorial, which is 1. And the right hand side is 2 factorial minus 1, which is also 1. and hence it is true. The inductive step will be, we have to use a hypothesis, inductive hypothesis, that is, this is true when n is equal to k. So using that, we have to prove that for p of k plus 1. So for p of k plus 1, the left-hand side will be all what we have in p of k plus the last term, which is k plus 1 factorial, which is nothing but the sum of the first k terms using the hypothesis. It will be k plus 1 factorial minus 1 plus the last term k plus 1 factorial. Pulling that k plus 1 factorial outside, we get 1 plus k plus 1 and then that minus 1. Simplifying the whole thing, we get that as k plus 1 factorial into k plus 2 minus 1. But this k plus 1 factorial times k plus 2 is nothing but k plus 2 factorial. So your p of k plus 1 will be k plus 2 factorial minus 1, which should be the right hand side of p of k plus 1. So this identity, p of k plus 1, is also true, and that's what we have to prove. So we have proved the second identity also here, which is true. And in this video, we proved that we can use the mathematical induction method to prove formulas or identities, and we showed the mathematical induction principle for proving two different identities. Hope this video was helpful. Thank you for listening, and thank you for supporting this type of video. Thank you for watching. Thank you.